Here we have an example taken right from your textbook, but I think it's very instructive for a couple of reasons. One is to allow us to actually take a real life situation where we have a copper wire, the radius of the wire, 900 microns is the radius, so typical wire with 17 milliamps flowing through it, to calculate the actual speed of the electrons in this wire when the current is flowing at 17 milliamps. Now, you definitely will not have to memorize the specific values for the molar masses or the density for materials, but you will have to be able to do the dimensional analysis if you are given the numbers to be able to calculate the number density as it shows here. So I kind of want to walk you through this quickly. So the number density you might have to calculate if you were given Avogadro's number, the molar mass, and the density of the material, in this case copper, to show you how the dimensional analysis works out quickly. If we're going to look at the number density, so the number per meter cubed, Avogadro's number is the number of anything per mole, and we're going to multiply that by the molar mass for copper, so that's going to be 1 on kilograms per mole, so immediately now we lose moles, and then if we were given the density of copper, density is kilograms, right, per meter cubed, we would lose the kilograms, and then of course we have our answer. The number density is the number per meter cubed, and that's really all that is shown up here. So we get the number density, so you would be expected to be able to do that dimensional analysis if required. And then of course I equals QNav, so that's really the equation we're looking at here. We're going to take this number density and use it here. I equals QNav, I divided by A is how they present it here, but we can solve it then for the speed, and when we plug in the numbers that we're given, the 17 milliamps, we use the radius of the wire is the 900 microns to get the pi r squared, we see that we get a drift velocity of 4.9 times 10 to the minus 7 meters per second, so exceedingly slow, right? So it's 1.8 millimeters per hour, and again, we've talked about this, but if we think about what is it that allows electricity to happen really instantly, and for us at the speed of light, it's not the flow of the electrons. It's the appearance, it's the flow of the electric field down the wire. And please get this bit into your notes, because this will be important in terms of really having a firm foundation of what's actually going on in the wire. The individual points of the wire themselves, right, do not see high and low voltage. So all of those conduction band electrons feel the presence of the electric field at once, and each electron feels that equivalent voltage pressure moving. And then, of course, because these electrons are in the lattice structure of the wire that's at a temperature that's relatively warm with respect to the amount of movement that is going on within the wire, that doesn't allow just the flow of electrons to move at an exceedingly fast speed. They want to, but they're almost instantaneously stopped, and we'll see a little bit more about that when we talk about resistance later on in this chapter as well. So please get this into your notes. I think it's instructive. You will have to be responsible for doing the dimensional analysis, but understanding that it's that instantaneous, or at the speed of light, presence of the electric field in the wire that is allowing electricity to do what it does instantaneously for us, I think is important.